A very good afternoon to all of you. Myself, Pankaj Chatterjee, and my colleague Ankuratri are going to present before you a paper which is an FPGA-based neutron radiation tolerant microcontroller. These are the contents that we'll be going through this whole presentation. So first of all, we'll start with the reason for which we have chosen this topic. See, in all the high technological and research applications, the electronic circuitry and its environment plays a very important and vital role. For example, in the space and satellite technology, the electronic circuits are in the prolonged exposure to the cosmic rays. And simultaneously, we take an example of linear accelerators that are being used in the medical science. These are also in the prolonged exposure to different types of radiation. Now, this prolonged exposure to this radiation generates severe types of several errors, which needs to be acknowledged. Now, these errors are basically generated in the electronic circuits consisting of microcontroller units. In it, the neutron radiation effect is the main dominating effect, and due to this, the neutron comes across the semiconductor device into the two metals, like in the direct one and the indirect one. In the case of the direct one, actually the neutron it has no charge, and due to this it has no charge, it cannot be interact with the semiconductor directly, or we can say it cannot be interact with it electrically. So it can be only interact with the semiconductor just by the lattice collision, and due to this there is resistivity has been changed and the degradation in the transistor gain. But in the condition of the indirect one, actually the neutron it reacts with the boron and it gives the lithium and the helium. And it mainly the outcoming is the helium, and due to this it triggers the single event effect. This single event effect it can be categorized into a two parts, that is the firm error and the soft error. This firm error it is the most severe problem than the soft error, and this firm error it causes the permanent damage of the device. But this is not in the case of the soft error. This soft error it actually change the functionality and the logical state of the device, and it can be categorized into a two parts, that is the single event upset and the single event transient. What is the single event transient? Single event transient actually is caused by the ionization particles, and due to this it will affect the combinational circuit. And in the case, it can be covered up itself by simply the transient changes in the voltage level on the signal line. Now the SEU, that is the single event offset. The single event offset actually it will distort the data which is stored in the cell. It is called the bit flip, and this the cosmic ray is coming in it, and there is ionization process takes place, and due to this functionality and logical state of the device has been changed. Now the next, it is basically concerned with the data storage element, that is the static RAM, dynamic RAM, and the flip-flop, and it also generates a serious problem in the SRAM-based FPGA. Why the SRAM-based FPGA? Because this SRAM-based FPGA, it is SRAM, it has a high vulnerability to the neutron radiation. Now, what is the FPGA? FPGA is unique stands for the field programmable gate array. This it consists of the three main parts: input-output port, logical blocks, and the last one interconnection wire and the switches. Why it is known as the field programmer? Because it can be configured according to the customer or the designer after the manufacturing, and it is configured in the hybrid description language. And these diagrams of the FPGA are shown. Okay, friends. Now coming back to the errors. The errors can be eliminated by applying several techniques, but the techniques which we'll explain here are concerned to the electronic circuit, which we will further apply to the microcontroller units. Okay, so these techniques of controlling the radiation error can be categorized into four parts. First of all, we'll start with the hardening by technology. It's a very initial level of technique, and it is being applied to the lowest technological level. Because we know that in every electronic device in the nowadays are having the basic components as transistors and cells. So what we do is we alter the structure of the transistors and we modify the cells, and ultimately we get a modification scenario of the electronic device at the manufacturing level. And in the second technique,